Good afternoon, everybody. And it's my great pleasure to welcome Carlos Rodriguez here from RINA, where he's head of yield and performance. And today he actually will give a talk of his previous work, because he did his PhD at CERES, at the National University of Singapore. And that's where we actually met.
Yeah, exactly.
When I was still at CERES, I was basically finishing up. I had an interview with Carlos, and unfortunately we were not working together at that time, but he completed his PhD at NUS and decided then to stay, become group leader in the systems cluster, working on performance. And CERES is one of the world leaders in floating solar, because they don't have a lot of roof space. So they look at covering water with solar cells, with modules, of course. And they're really the world leaders in this field. So I'm really looking forward to your presentations about the potential and challenges for floating. So
sure.
Carlos, the floor is yours.
Thank you so much, Prof. And yes, just to highlight on that point, it's very funny. When I was just joining NUS and CERES for my PhD, Prof. Brown was leaving. So I'm happy that maybe after 8 years, I finally was able to meet him in person at least. So just to start, I wanted to say thank you to SPREE and to UNSW to have this opportunity for me to share a little about the knowledge gathered on floating PV. I will be discussing about their potential, status, and challenges from a worldwide perspective, but also for Australian perspective, just to see where it makes sense to go for floating here, or actually not really. So let's start with it. First of all, I just wanted to highlight a little bit about my current company. So I'm currently the head of yield and performance at RINA. RINA is a company that is not that young anymore. It's actually more than 150 years old, and we are headquartered in Italy. So actually, we are a company that have different kind of services regarding marine applications, certifications, infrastructure and mobility, industry, real estate, and the key topic of today's discussion, the energy division. We have more than 9 nationalities. We have a high percentage of educated people. High degree level people, sorry. And you can see that our average age is over 40 years old, so I think a little higher than most of your age, actually. Just to highlight a little about the work we tend to do, we have offices in different countries. We have roughly 70 offices located worldwide. And the kind of work we do when it comes to energy projects, you can see that most of our work is actually centered in Europe, because our headquarters are in Europe, so we always started there. But then we expanded throughout the world. So now we, of course, have divisions here in Australia. We have an office in Melbourne. We have also an office in Sydney. We are aiming to expand a little more in Australia and also in New Zealand to take over more of this region. This image shows a little of the work we have been doing only when it comes to the green energy solutions, where the yellow countries are the ones where we have worked in different projects from those locations. And the circles show you our offices worldwide. So we actually work in different kind of projects regarding renewable energy, a lot into solar, wind, energy storage systems. We also have interest to work in hydrogen-related projects and so on. So on this point, I also want to share that renewable energy, as you guys already know, the potential keeps on increasing, the deployment keeps on increasing, so there is even more projects, there is even more work. And that's also why even for consultancy companies like RINA, we are always looking forward to get more and more people to join our company. So after you finish your studies in UNSW, if you are interested, by all means, feel free to contact us. We will be more than happy to discuss whether there can be some potential opportunities, because at the system level, renewables in Australia is a huge market. There is huge potential. There are just too many projects. And even when it comes to the different projects, we actually work on the different stages on the project. Even from the very beginning to the design and the permitting, when you want to do an installation, when it comes to the procurement part, when it comes to the construction of the project and operation and maintenance, and even all the way to data analysis. So actually our range of work covers the whole stages when it comes to these deployments. Okay, now I can focus a little more about the topic that I want to discuss today, that is about floating PV. So something very important I want to highlight first is that floating PV, when I talk here about floating PV, I don't mean that it's any system where the solar panels are on top of water, because actually you have another kind of system that are the pile or steel-based PV systems. So floating PV, the definition is that you actually need to have a floater. You need something that is floating on water, which is, for example, the image that you see here on the left. You see here, these are some floats, some pure floats, and on top of them goes the solar panels. On the other side, other kind of systems that are also installed on top of the water are the pile or steel-based, which literally you have a pile here. So a fixed structure, and then you install the solar panels on top. Just to highlight that, in this whole presentation, we focus about floating PV. And the pile or steel-based PV systems, actually, the current installation capacity is way larger than the one of floating PV. While the largest floating PV system in the whole world so far is of around 300 megawatt peak, the pile steel-based PV system can easily reach more than 500 megawatt peak. So most of the projects that are on top of water are actually of this design. Each one have their own advantages, each one have their own disadvantages. Like for example, for the pile or steel-based system, you will normally use this kind of installations in shallow water, typically when the water depth is below 5 meters, and when the water variation is not that big. Why? Because if you are very unlucky and the water level keeps on increasing, then the water might reach the solar panels, the water might reach the combiner box, might reach the electrical cables, and then you are in trouble. But in places where you have a higher water variation, you have larger water depth, then it tends to be more cost effective to use a floating application, because if the water level increases, then simply the floater will also go up. It's just a matter of a design of the anchoring and mooring. So depending on the case, depending on the project type, one of these applications will be more cost effective. Historically, pile and steel-based have way more years of deployment, and floating is relatively new in comparison. But this is quite an exciting topic, and this is the whole point I will be discussing today about floating PV. Just wanted to make this distinction first. Now, when it comes to floating PV, even though maybe around 10 years ago the first installations started, right now we have many systems that are very large, are already PV farms, are already utility scale floating PV systems. And these are some examples. The one you see here on the top left that is installed in China, to the best of my knowledge, this is the current world's largest floating PV system installed in the whole world. That is of 320 megawatt peak. Then there are other kind of systems that are very large, like for example this very cute one from China, where you have the very nice panda that is of roughly 100 megawatt peak. And of course you have installations in different parts of the world, in different countries. And just wanted to highlight also this one that is in Singapore, that is of 60 megawatt peak. Yep. So when it comes to floating PV, there are different types. Actually, there are more than 70 manufacturers of floating PV systems. Each one tries to come with their own solution, with their own advantage, with their own unique selling point. But more or less, this can be grouped in 4 different categories. The first category, that is by far the most popular one, that is the one that is used in most of the projects, at least till now, that is the pure float-based systems. That are the ones that you see here. This is practically the floater, and is composed by pure float, meaning that there is no metallic or rail interconnection between float to float. So with this kind of design, you are actually able to reduce the cost, but then you need to be aware of the mechanical stability of the system. But this is the kind of solution that is currently mostly used. Besides this one, there is another one where now you still have the floater. You need something to float. That is, for example, in this image are the blue floaters. But now you combine the floaters, typically with a structure like a metal or a reinforced plastic structure, in order to be able to keep the solar panels more static. So then they have more better mechanical properties. So the panels will not shake that much due to wave influence, for example. This is another solution that is used by different companies. Then there is a third one that a few companies try to use it, that is the membrane or mat-based solution, where practically what you do is you have a membrane, you put it on top of the water, then you just put the solar panel on top of the membrane. Typically the solar panels will be horizontally. So you can think that maybe if you are very far from the equator, that might be a little bit of a disadvantage. That being said, because you have the solar panel typically in contact with the membrane, and then the membrane is typically in contact with the water, and the water temperature is typically very low, then you will have some extra energy gain due to the extra cooling effect. And finally, the other one that I wanted to highlight that is the semi-closed solution, where what they are practically aiming to do here is you have a floater, but on top of the floater you use, for example, cement material in order to practically have extra land here. You practically create artificial land that is floating, and then on top of it you can do an installation very similar to the one you will do for land-based PV system. So again, all of them have their own unique selling points. All of them have their own advantages and disadvantages when it comes to cost, when it comes to reliability, when it comes to performance. So different companies are trying to focus on different points when it comes to this. Now, why there is still floating PV? Why now floating PV is becoming a hot topic? It's because in principle it can give different kind of advantages. The first one, as Prof. Brown already mentioned, in particular for countries or locations when land cost is very high, when there is some land constraint, then in principle this kind of system need not at all or need a little bit only of land, because most of the installation will be on the water. Like for example, Prof. Brown already mentioned about series, because indeed Singapore is a country where you have limitation when it comes to space. The previous system I showed of 60 megawatt peak in Singapore is, for example, the largest PV installation in the country. To the best of my knowledge, Singapore is the only country in the world where the largest PV system is a floating PV system that is of 60 megawatt peak. So maybe you might already be thinking, okay, but Australia might not have any land requirement. But there are other points to focus on this. The second advantage is that there can be a potential for performance gain. That means a better performance ratio, lower losses, so better energy production. This is typically attributed because it's expected that the temperature loss, that means the temperature of the solar panel, will reduce. If the temperature of the solar panel is lower, this means that they are able to work at higher efficiency. Now, the reason why the temperature of the solar panel reduces, the main factor, is still an open topic that is still discussed. And different researchers are trying to prove which is the main factor. Like for example, there is some opinions which says that the main factor to reduce the temperature of this kind of installation is simply because when you install a floating PV system, normally you will not have buildings nearby. Normally you will not have objects that will block the wind, meaning you will have more wind. And if you have more wind, you will have a higher cooling effect. Other people tend to say that the main reason is actually because you have the solar panel on top of water. When part of the water evaporates, some of the water particles will attach to the rear side of the panel, and then there will be a temperature difference, so there will be some thermal transfer from the solar panel into these water particles, and that this might be the main factor to reduce the temperature of the panels. Then there is the third point that simply says that because the temperature of the solar panel is higher than the temperature of the water, there will just be a thermal transfer because of the temperature difference. So to be honest, these three factors are valid, and these three factors will take place when it comes to floating PV system. But it is still to be confirmed which is the main factor and by how much. It likely will simply depend on the site, on the project specific, which of these factors will be the main factor that will affect the energy production. Just to give you an idea, there is a lot of research based on real data that suggests that the typical extra energy of floating PV system versus a typical land-based system is between 5 to 10% extra energy that the floating PV system can produce. Again, depends on the technology, depends on the location, depends on many factors, but this is just a general idea. At the same time, normally you are expected to have less shading losses when you use a floating PV system. Why? Again, normally you will not have buildings, you will not have trees, you will not have objects that are typically that can produce some shading on these systems. Normally you are just surrounded by water only, and the water is also flat, it's uniform. For the same reason, you will expect less soiling losses. That being said, and to be fair, in many of these projects, even though you have less soiling losses due to dust, you might have higher soiling losses due to bird dropping. Because there are many projects where actually on the location where the floating PV system is installed, there are large birds that live there. And normally large birds come with large dropping. So this is a typical issue with floating PV system. It's very normal when people try to do the design of a floating PV system that the question comes on how can we mitigate these losses. So it's also an open topic. There are different solutions to try to mitigate this issue, but yeah, is to try based on the project specification, case by case only. Regarding the potential environmental benefit, this is a key topic that can also be advantage and disadvantage or challenge, because there are many concerns when it comes to the environmental impact of floating PV on the water and on the biodiversity. But at least many studies have shown that by having floating PV, practically you are blocking part of the light that normally will impact on the water, you are blocking it with the solar panels. Because of that, you will reduce the algae production. And in many locations, this is a desirable property to reduce the algae production. Okay? And at the same time, because by having solar panels on top of water, you are blocking part of the light that is hitting the water. So you will expect that the water evaporation will be reduced. So by having floating PV, you can preserve some of the water. In principle, there are different, and I will show later, there are different estimations to try to find out by how much you can preserve the water. And this is very useful. For example, if you think about it, if you have a hydropower plant. For a hydropower plant, you want to have a lot of water accumulated in order later to convert that water from potential energy into kinetic energy, then you produce into electricity. So in many hydropower plants, there is a lot of interest to have solar panels, floating solar panels, in order to try to keep more and more water to later use it for energy production. So floating PV and hydropower can actually work together hand by hand. At the same time, if you are in a location where, for example, you have a source of water that is very important, let's say, for water, for humans, for water consumption, you also want to accumulate that water as much as possible. And this is one key interest for Australia, for example. There are many potential projects in Australia where people are thinking whether, in order to try to save as much as water from many of the reservoirs from this country, if they should just deploy, let's just say, a big mat, just to cover the sunlight. But one potential solution instead of this can be to deploy a floating PV that can block part of the sunlight, so you can still have some water savings, but at the same time you can produce electricity. And maybe from this angle, it can be of interest to Australia. Now, nothing is perfect, otherwise we will be surrounded by floating PV. And all technologies come with advantages, all technologies come with challenges or disadvantages. What are the typical challenges expected in floating PV? First, while PV, the field of PV already has quite many years, floating PV, when it started with the mass deployment, it happened maybe just within the last 10 years or so. So it's still considered a relative new technology. So there is still a lot of questions or a lot of confirmation that needs to be done based on real system, real data gathering that people are still trying to get more and more in order to try to prove whether the system is reliable, whether the system can last for 25, 30 years, or whether the system will affect the environment among other factors. So one key challenge is that it's still a relative new technology. Another point is, like, in principle, floating PV, the cost of installation of floating PV tends to be higher than the cost of installation of standard PV for ground-mounted systems. While it's true that the cost of floating PV has reduced quite a lot in time, even till now, for most of the projects, the cost of floating PV is still higher, a little higher than the cost of land-based PV system. Of course, then you need to compare with the extra energy that you expect to produce from floating PV. You combine both, typically in the levelized cost of electricity, and then based on that, you can really see which technology makes more sense. We have had some projects where, for example, there is water available, there is also land available, and the investor is asking us which installation makes more sense from the CapEx perspective, from the OpEx perspective, from the levelized cost of electricity, from the return of investment perspective. So there are many factors that need to be considered to try to find out which is the best solution for that particular project. Another challenge is that if you think about it, if you install a PV system on land, a ground-mounted PV system, normally you will have the mounting structure, and then you have the solar panels on top of the mounting structure. So in principle, the mounting structure is very well designed to handle wind, to handle some mechanical constraints. But if you install a solar panel on top of a floater, and the floater is moving, then you will have more mechanical constraints. You are concerned on whether the system will be stable enough. where the system is able to handle strong winds, is able to handle a strong wave, and so on. So because of this, it's very normal that for floating PV system, even if you are in locations that are far from the equator, normally they will try to restrict the maximum tilt angle of the PV system. Typically is 10 degrees tilt or 20 degrees tilt for typical systems. So based on this, if you are aware of the rule of thumb that says that in principle, in order to have the highest energy production, in principle, the tilt of your PV system should be similar to the latitude location. So if you are very far from the equator, you in principle want to install solar panels with higher tilt. But higher tilt means that you have a higher surface area that will be impacted by the wind. And if you have the floaters, they might not be stable enough in order to keep the solar panel without moving. So that's why there are concerns, and they try, many solutions providers, they try to restrict their system to up to 10 or 20 degrees tilt. This is the typical, at least till now. I will assume that in time, they do more work, they improve their solution, so the maximum tilt will keep on increasing. Another key point is also when it comes to guidelines and standards. There are already some attempts on standards and guidelines when it comes to the installation and maintenance of floating PV system. But there is still a lot of work to be done on it in order to have full international standards to assure that a proper system is installed. And also, and I will discuss a little bit about later regarding operation and maintenance and degradation concerns. So you can think it about this way. Again, it's always good to compare with land-based PV system. If you have typically a land-based, a ground-mounted PV system, if there is an issue with one solar panel, if there is an issue with one cable that connects one panel with one panel, you are in principle able to easily walk and reach that panel. You can even go below the solar panel. Typically, panels for ground-mounted system are installed, let's say, 1+ meter above ground, 2 meters above ground, and so on. So you can easily reach the panels. You can easily reach the cables. But imagine if you have an issue here. The inverter tells you that there is an issue with one particular string or with one cable from one of these strings. Just imagine if you are here, how are you able to reach, for example, this solar panel? So normally they will put floaters in the middle in order for people to walk there. But even with that, you need to walk very slowly because you don't want to fall down. And even in order to find an issue right away, it's very difficult because the panels are very close to the water. So for operation and maintenance, it also tends to be more challenging in comparison to ground-mounted PV system. Of course, maybe this kind of solution will be more ideal when it comes to operation and maintenance, but each one comes with their own advantage and disadvantage. Okay. Degradation concern, I will talk about it later, but it's mostly by the fact that now you're surrounded by water. Now you have more humidity. So it means that the concern is that you might have more water ingress into the solar panel, into the solar cell, but can act as degradation points, recombination points, sorry, and that can affect the degradation. And finally, when it comes to the warranty, if you are aware, when you buy solar panels or when you buy inverters, normally they come by default with a certain warranty. But you need to read what is the warranty conditions. So you need to be sure that the solar panel provider, the inverter provider, and so on, also assure that this warranty can also be applied for floating PV applications. Just to give you some examples, normally most of the system by far for floating PV are inland reservoirs, so it's for reservoirs itself. But now there is a tendency to try to do work or installation for offshore. So now we are in open sea. We have seen many cases where many of the manufacturers are not willing to extend their warranty right away for offshore applications because there is still a lot of knowledge to be learned when it comes to these systems because the challenge for the weather condition becomes more critical. So nothing is perfect in life. You have good things and bad things. Now, I just wanted to put some things into perspective and to discuss about what is the current installation capacity when it comes to floating PV. What you see here is the red bars tells you how much floating PV was installed for that year in the whole world. And the unit is in gigawatt peak, watt, kilo, mega, giga. So you can see that roughly there is an increase of installation capacity year after year. That means that there is, in principle, more adoption of floating PV year after year because people start getting trusting more on this technology because now there are previous projects that have survived and then there is some lessons learned there is some knowledge that is created now based on the previous projects, and now you are more confident to invest in new projects. Now, the next bar, it shows you, the blue bar, is the historical accumulated installation capacity for floating PV, meaning, for example, the bar for 2020, that is the blue bar, tells you since beginning of time, all the way till 2020, how much floating PV has been installed in the whole world. So then you can see that the increase like this is roughly exponential increase. Actually, the tendency is very similar to the one of pure PV system. So this is something good when it comes to floating PV, to see that actually there is more and more installations happening for floating PV applications. Now, just to give you an idea, from the previous slide, we see that at least till 2022, till end of 2022, the total installation capacity of floating PV is of around 6 gigawatt peak. Then the key question is, how much is 6 gigawatt peak? How big it is actually? Now, when it comes to the unit watt peak, I'm sure there is already good knowledge on what it means watt peak, which is simply the power that a system will produce under the standard testing conditions. So you need to have these three conditions in order to say that your system is able to produce, the total system capacity is able to produce 6 gigawatt. Just to give you an idea of how big is this number or how small is this number, I can just try with some basic reference. Like for example, 1 megawatt peak roughly will be 2,500 solar panels. Of course, if you use panels with better efficiency, with better power, then this number will go down. But just to have a general rule of thumb, 1 megawatt peak is roughly 2,500 solar panels, which based on its area is roughly 1 football field. So 1 megawatt peak is 1 football field. Now, so far, for floating PV, it has been installed a total of 6 gigawatt peak. 6 gigawatt peak will mean that in total it has been installed around 15 million solar panels in the whole world, floating on the water. Hopefully it's still floating till now. Now, when you have this number, okay, how big is million? Like now I have 1,000, then I have million. How big is this number? When it comes to the area, it's of roughly 30 kilometers square. Now, based on what I searched in Google, based on the size of UNSW main campus, this will mean that the total floating PV installation capacity is around 80 times the main campus of UNSW, just to give you an idea of how big this is. And if you can notice, most of the installation started since roughly 2015. So it has been, what, maybe 9 years, since roughly 9-10 years ago, floating PV was seriously going into deployment. Before, there was just mostly test beds. People were just trying to see where they can last. But only since roughly 2015, 2014 is that things started to be more taken into account, and then you see the big numbers. So that's why it's still considered that this technology is still relatively new. Okay. Now, just also to put things into context, because floating PV has advantages, also disadvantages. I want to share as much as I can. When it comes to the overall deployment of floating PV, if you superimpose it with the overall deployment of PV, meaning ground-mounted, rooftop floating PV, building integrated photovoltaics, as long as there is a solar panel, then you have this plot. The blue bar shows you the historical accumulated capacity of all kinds of PV systems. And the red bar that you might not be able to see shows you the total accumulated installation capacity of floating PV system, which, if you see, maybe you see something reddish here. So this is the comparison. Now, just to also put things into more perspective, you have this line. What this line shows you is the share of installation capacity of the whole PV that belongs to floating PV. So you can see that from the whole PV, in the very beginning, floating PV was almost nothing, and then it started increasing. Now this trend looks very nice, looks large, but then you see the maximum number, 0.5%. This means that by end of 2022, out of all the PV systems installed in the world, roughly 0.5% of those systems were floating PV. So there is still a lot to be done in floating PV in order to be even a main, to have a higher share, but you can see the trend is increasing. Even if it's roughly 0.1% per year, it's increasing. So let's see how far it goes. Now, I also wanted to share a little bit when it comes to the technologies being used for floating PV systems. One key topic is regarding monofacial and bifacial solar panels. Just to be clear, when I refer to monofacial panels, simply means that the panel is able to absorb sunlight on the front side only. While bifacial solar panels, you can absorb on the front side and on the rear side. Now, bifacial panels, maybe 10 years ago, there were not many used for real deployments. Why? Because the price was very high in comparison to monofacial. But the beauty of life is that you just need to live long enough in order to see the cost reduction. So bifacial panels kept on reducing in time. And right now, even though bifacial panels might still be a little more expensive than monofacial for most of the cases, the difference is very minor. So it's very similar cost. And that's why the gentlemen from ITRPV have this trend. By 2023, they saw that roughly 50% of all the installations, of all the production, of panels were bifacial. Now they expect that for this year, 2024, it will be more than 50%. These are the predictions. This is what really happened by 2023. So it's expected that bifacial panels will take over the market. Why? Again, now the cost is extremely close to the one of monofacial, but by having a bifacial panel, you have extra advantages. Like, for example, you have, in principle, extra energy production because now you can absorb light in the rear side. But let's see what happens if you use bifacial panels for floating PV systems. Normally, in order to have a bifacial solar panel, in order to produce the highest energy, wants to fulfill 3 conditions. The first condition is you want high albedo values. What is the albedo? It's simply the percentage of light. When light impacts a surface, how much of that light is reflected outwards. So that percentage is the albedo. When you have a bifacial panel, you want light to reach the rear side. So in principle, you want light to hit a surface and then be reflected to the rear side of the solar panel. The albedo irradiance is typically the highest component of irradiance that reaches the rear side of a bifacial solar panel. So you want high reflectance. So ideally, you want to install bifacial panels in snow, where the albedo is very, very high. But what happened? In water, like if you see this measurement done by Ceres, they see that the typical albedo of water was below 10%. So it's not as high as with other surfaces. Now, also, when you have a bifacial panel, if you think about it, if you want to absorb more irradiance at the rear side, you want a high tilt angle. So you have higher surface effective area to interact with the ground, with the reflectance. But what happens when it comes to floating PV system, as I mentioned before, there are mechanical constraints. So typically, you will have a limitation on the tilt. And that's why typically the tilt of floating PV systems is less or equal to 20 degrees. So it's not advantageous for bifacial. And finally, again, if you want to have more irradiance at the rear side, you want to install bifacial panels with a high height from ground. So the effective area that they can see, surface area, increases. So you are able to absorb more irradiance at the rear side. But again, if you see this image of a typical floating PV system, you will see that the solar panel is installed very close from the surface, from the water, typically below 50 centimeters. So based on these points, it seems that bifacial solar panels are not the best option when it comes to floating PV system. That being said, most of the floating PV systems I have seen or I have worked with employ or aim to employ bifacial solar panels. Why? The first reason is that even though it's a smaller energy, you still have a extra energy production. Even if it's just 1%, 2% extra, sometimes it's useful. Like for example, in a place like Singapore, where you need to make every meter square count as much as possible. You need to squeeze it as much as possible. So in this kind of location, when you have land constraints or even water constraints when it comes to space, you want to get the most energy, the highest energy as possible. So then even if bifacial just give you a small percentage of gain, it's still worth it for many projects. But one of the key reasons is because if you think about it, typical monofacial panels, they have glass on the front side, and then they have a polymer backsheet on the rear side. While typical bifacial panels are glass-glass. So there are many studies that have shown, I think some studies also done in UNSW, that have shown that the glass at the rear side is a better insulation layer in order to avoid for particles to enter the solar panel that can enter the solar cell and act as the recombination points that can increase the degradation. So it is expected that if you use, not really bifacial, but if you use glass panels, then the degradation of these panels in this kind of environment that are of high humidity, the degradation will not be that high. And this is a big concern for many investors that is still to be fully proven, actually. So there is some work on this, but again, there are not many floating PV systems that have many, many years of collected data in order to accurately prove this point. But because of this, many people are actually aiming to use glass panels that are typical bifacial panels. Just to give you an idea, even if you see data sheets of different manufacturers, when you have some free time, you can try to do it. There are many cases where the manufacturers offer you the same technology, let's say PERC. They offer you monofacial version, and they offer you bifacial version. Open the two data sheets, and you compare the degradation value, and you will see that typically the degradation warranty percentage per year of the bifacial is lower than the degradation warranty of the monofacial. And also typically that the years of warranty that they give you for bifacial is typically 30, which is higher than the one of monofacial that is typically 25 years. At least when it comes to many PERC technologies, I see this trend quite a lot. I still need to check more when it comes to TOPCon, heterojunction, whether this trend is still there. But this is mostly because you have glass at the rear side. Of course, you have extra glass, you might have extra weight, so you also need to watch out with that. Now, when it comes to degradation, I wanted to show one key research that was done by previous colleagues from SERIS, that they actually have a test bed here, so all credit goes to them. They actually have a test bed in Tenggel Reservoir in Singapore that you can see the different floating PV systems looks a little different. It's because they have different technologies. So they actually tested and used the data. I think they used roughly 3.5 years of data in order to estimate the degradation of these systems. And the degradation you see here for different strings of different systems. You see there are three values. It's because they use different degradation approaches. And what they concluded is that actually, for most of the cases, the degradation during these 3.5 years or so is within the warranty provided by the manufacturer. So at least in this work, they saw that there is not a big degradation factor that will be around here, for example. But again, this is just one work using a few years of data. It's still needed to have even more work from other systems, from other sites, to also corroborate this, and also to have a better idea of the degradation on floating PV systems. It's still quite a hot topic. And normally you need a test bed. You need to collect data, you need to wait a few years, and then you can start trying to do these plots. And hopefully by then, the technology you are testing is still on the market. That's also one typical challenge of having test beds. But yeah, this is quite an interesting work to show you a little more about the degradation of floating PV systems. Now, I wanted to share a little of the work I have been doing together with colleagues from other institutions. So what I will be showing here is one work where we are analyzing the potential of floating PV for inland reservoirs in the whole world. So I think it's of around 200,000 plus reservoirs in the whole world that we are analyzing the potential if you deploy floating PV solutions. This is a publication that we are currently submitting into Joule, that we are on the second round of revision, so finger crossed on that one. But for this presentation, I just wanted to show on some results when it comes to Australia only. So when it comes to Australia, we actually analyzed a total of around 1,500 reservoirs all over Australia. And then and when it comes to these reservoirs, just to give you an idea, when it comes to the size of the reservoir, you can see this is the number of reservoirs for this range of area of the reservoir in hectares. Then you can see that most of the reservoirs are actually below 500 hectares, most of them in Australia. That being said, if you add the whole area, then you have this other plot. And then you can see that even though there are fewer reservoirs that are of high area, of course, their potential is way higher if you want to deploy floating PV system in them. Okay? So I just wanted to share a few results that we did here when analyzing these reservoirs. First one is regarding the energy production. In principle, you want to install systems that are able to produce high energy. Now, for this presentation, I'm showing the results from 4 technologies only. The first technology is what happens if you install solar panels at horizontal position. That's FX0, fixed tilt, 0 degrees tilt. The next one is what happens if you install solar panels at a fixed tilt of 10 degrees. Solar panels at fixed tilt of 20 degrees, and what happens if, just for comparison's sake, you install solar panels using the traditional rule of thumb, where the tilt of the solar panel will be equal to the latitude location. Just as a comparison. So what you see here is the latitude range for Australia. I saw it's roughly from -9 degrees all the way to roughly -45 degrees or so. That covers the whole Australian territory. So we analyze the whole latitude range, and then we make the average in order to see per latitude location roughly how much is the energy production. So we see first that when you install solar panels at horizontal position, normally you see that the energy production is lower than the one from the others. Why? You can simply just use the usual rule of thumb that says that to have the highest energy, in principle, you want to install with the tilt equal to the latitude. So if we are at a latitude of 10 degrees south, and you are using horizontal, that means position, then you have some energy loss. And you can see that that loss tends to decrease, of course, the further you go from the equator. Then you have even more losses when you install solar panels at horizontal position. That being said, if you then install solar panels with a fixed tilt of 10 degrees, that is the green line here, you can see that then you have a higher energy production, but roughly when you reach about 15 degrees of latitude, minus 15 degrees of latitude, then you can see a gap with respect to the other technologies. So you can see that roughly the rule of thumb seems to be accurate, because in principle, if you want to have an installation with 10 degrees tilt, you should be at a latitude location of around 10 degrees, so around here, to have the most of it. Then if you use now the other solution, that now you have solar panels with 20 degrees tilt, you can see that actually this one have almost the same results as the one of fixed tilt at 10 degrees since the very beginning, but later it have extra energy production when you go farther from the equator. And finally, if you compare with the so-called ideal design, when the tilt is equal to the latitude, you can see that indeed, for highest latitude location, it will produce more energy. But the difference between that and the one of 20 degrees tilt is very similar. So even though there will be losses, energy difference is not as big. Of course, in principle, we want to produce as much as energy as possible. But this gives you an idea that, at least in Australia, solutions of floating PV with a fixed tilt of 20 degrees tilt seems to be quite good already. Of course, if you go farther into latitude, you go more to the south, then this gap will keep on increasing. But at least for the Australian location, seems to be, in principle, good enough. Now, this is regarding the total energy production if you use monofacial solar panels. But the key thing is that we also mentioned that you can also have bifacial solar panels. Bifacial solar panels, the extra energy comes from the extra irradiance at the rear side. If you compare the extra energy production of a bifacial panel versus the monofacial panel, that's what we call the bifaciality gain. So this means how much extra energy you have if you use a bifacial panel instead of a monofacial. So you can see that for most of the solutions, actually the bifacial gain tends to be low. And this is the key thing I wanted to highlight, I highlighted before. So for most of the solutions, the bifacial gain is below 2%. But if you use fixed equal to latitude, that normally the tilt will keep on increasing, and that is helpful for the bifacial gain. And that's why you can even reach bifacial gains if you go to the very south of Australia of around 5% extra energy production. Where are we located now? I think, are we located around here? Mm-hmm. Okay, so roughly 3%, roughly between 2 to 3%, thank you. So it's still quite a decent number. I remember in other countries that are closer to the equator, you can have even lower gains. So it depends on the locations, on the specifics of the projects. And again, in principle, you want to squeeze as much as electrons as possible to produce as much as energy as possible. But this already gives you an idea of, by using different solutions, different designs, their advantage and disadvantage. Now, this graph looks nice, but let's put some numbers on it. So when it comes to Australia again, if we install, normally if you have reservoirs and you are a PV person, you might say, okay, let's fully fill this reservoir with solar panels. Maybe that's not the best decision because it might affect the biodiversity, might affect touristic activities, and so on. So there are still some rule of thumb that people are trying to come with to try to tell you what should be the maximum deployment of floating PV per reservoir. Truly speaking, it depends a lot on the location, it depends a lot of the fauna, the biodiversity, the social impact, and so on. But in principle, many cases, if you have a reservoir and you only fill 10% of that reservoir with floating PV, for most of the cases, it tends to be okay. But it's just a general rule, but it's not a rule for all cases. So that's why for all of these 1,500, roughly 1,500 reservoirs in Australia, we assume what happens if we fill 10% of their area with floating PV. So the total capacity will be of around 105 gigawatt peak. Just to give you an idea, in Australia till last year, the total PV installation capacity was of around 34 gigawatt peak. So it's roughly 3 times more if you just fill 10% of all reservoirs in Australia. Now the key thing more than the capacity is actually the energy production. These are the electrons that are flowing, how much energy you produce. And you can see when it comes from horizontal, this is the value. And of course, if you keep on increasing the tilt, the energy production increases. But then again, now it's tera, so now you have watt, kilo, mega, giga, tera. Then the question is, how big is this number? Just to give you an idea, when it comes to the electricity consumption in Australia, if you are able to produce this amount, you are able to satisfy roughly 68% of the electricity consumption in Australia. And then if you go for this other design, you are able to satisfy all the way till 3/4 of the electricity production in Australia. Now, maybe besides electricity production, a very important factor is water savings. Based on some approaches, we aim to estimate the water savings just by covering 10% of the reservoirs. And we saw that the water savings in Obra will be of around 1,800 kilometers square per year. This will represent roughly 11% of the water consumption in Australia. So I think this point is a critical point on why, for some cases, floating PV might be useful for Australia. Because again, in Australia, there is plenty of land, that is not the problem. But water availability, drinkable water availability, might be of higher interest. So this number might be of a higher interest when it comes for floating PV application in Australia. Okay. Now, just to finish this presentation, I wanted to discuss about the new hot topic in floating PV. Floating PV for inland reservoir have already been researched for roughly 10 years, or a little more than 10 years. But now the new hot topic is, let's go into open sea. Let's go for offshore floating PV. Different to inland floating PV that already we have utility scale solutions, for offshore floating PV, we still don't have big systems. They are still at the development stage. To the best of my knowledge, the largest offshore floating PV right now is from Ocean Sun, that are these 2 nice rings, in total of 500 kilowatt peak. But there is, to the best of my knowledge, there is no offshore, and by offshore I mean kilometers away from shore, not just at shore, that is near shore. If you go many kilometers away from shore, there is no system, to the best of my knowledge, that goes beyond 1 megawatt peak. So why? Because now the weather conditions are more challenging. Many of these are actually just test beds. You can see based on their size. So what are the typical challenges? The main one is mechanical complexities. Again, always remember that even though when you install a PV system and it goes to the news, everybody is happy, but then that system is supposed to last for 25, 30 years. And then it comes the real challenge. You want to be sure that your system is still there. You don't want it to sink down. So now, typically for offshore conditions, the wind and wave conditions are tougher than for inland reservoirs. So now you need to do designs that are more mechanically robust. Another typical limitation is now that you are in open sea, normally you are on the ocean, so you have salinity. This means that if, for example, you have a typical metal, it will be easily oxidized. So you need to also protect from it. At the same time, operation and maintenance. Imagine you have a system that is, I just show a number, 50 kilometers away from shore, and your sensor detected that there is an issue with one string. Then you need to ask one of your workers to swim 50 kilometers and go there to fix the issue. So operation and maintenance also becomes challenging from the distance that you need to travel in order to fix the issue, and also for the safety of your staff because of the weather conditions. As I mentioned before, warranty from some manufacturers is still a big concern. Many of the manufacturers are aiming to design specific solutions where they can assure their warranty for offshore conditions. But this is happening right now. And finally, losses, like mismatch losses. What I mean by this, imagine if you have solar panels connected in series to form the string. If you have a stronger wave, the panels will move the tilt a little bit. But because the wave is not uniform, this panel here that is connected in series with this panel might have this tilt like this, and then this one might have this tilt like this. So they both absorb different irradiance level. They both will have different short circuit current. So because they are connected in series, then they have the limitation based on the current. They must share the same current, and then they can have some losses, electrical losses. And this is what it means to this one. So that being said, even though there are challenges, there are many companies that are aiming to deploy their products for offshore PV. Why? The main advantage, you have a space. In principle, you will have as much as a space as you want in order to do your installation. So with that, you can really think about deploying huge systems because the space is normally not the issue. It's just that you want to be sure that the system survives. Just to give you an idea on the potential, and this one I will also show a work that I'm also doing with some other colleagues that is still to be submitted, so don't submit it before me. Here we are analyzing, in the previous work, we were analyzing the potential of inland floating PV. Here we are analyzing the potential of offshore floating PV. So you are under open sea. And for this, we are considering different factors that affect the installation design. The first one is, for example, wind speed conditions. So what you see here is the wind speed worldwide. And of course, in principle, you want to install your system in a place with low wind speed. So you don't need to apply many mechanical constraints. Your system can be cheaper, and you can be more relaxed that hopefully your system will survive. You can see that in principle, the low wind speed happens around the equator. Also wave height. So this system needs to have an anchoring and mooring design. This means that by that, they also have a limit when it comes to water variation. So if the wave heights are very big, some of the system might not be able to handle it. So you cannot go with one particular design based on the wave conditions, for example. What I show you here is, again, the wave height, and once more you see that close to the equator seems to be a nice place, in principle. Another one is the bathymetric condition. This means the water depth. At the end of the day, it's not that you leave the solar panel with the floater just there, otherwise it will just go away. You need anchoring and mooring. But if the water depth is very large, very big, you need to pay a lot for the anchoring and mooring solution. So this will affect your overall LCOE. So what you see here is for locations up to like 120 meters, these are these colors. So you can see if you go further, then it's more than 120 meters, so maybe it's not the best place to install floating PV for offshore, at least for now. People keep on improving their technology, so it's just a matter of time. Now, I just wanted to show here a little bit just to highlight about the potential for offshore. So this is the whole world. Okay? In blue, you see where you can install offshore floating PV. So if you apply no constraint, you can in principle apply everywhere you want. But let's start applying some basic constraints just to have an idea of the remaining area. If you want to remove regions where there is potential ice formation, now you have this area. So now in white are the regions that are removed due to apply constraints. I'm not saying that floating PV where there is location of ice formation is impossible. There are already inland floating PV in Switzerland, in China, in Japan that are installed in reservoirs that experience ice formation. It's just that it tends to be a little more challenging for the installation, for the operation maintenance, and so on. So for simplicity, we are removing this in order to try to reduce some of the issues when going for offshore floating PV. Second one, protected areas. Good luck trying to install a system which is a protected area. So in principle, we are also aiming to avoid those locations. Third one, wind speed. So there are many solutions. It depends on the manufacturer. There are some manufacturers that tell you my solution can handle up to 10 meters per second, up to 20 meters per second. We have seen solutions that they claim they can handle 20 plus meters per second. So that's why for now we are using this constraint, just to have an idea. This can of course change based on the particular solution you are aiming for. Wave height, less than 10 meters. Again, I have seen some manufacturers that claim that their solution can handle up to, let's say, 8 meters, 9 meters, and so on. So for simplicity, just to give a little more relaxation on the constraint, I'm assuming no more than 10 meters wave height. And finally, water depth. There are floating PV that have been installed in water depth of like 70 meters, 80 meters, and so on. So again, 100 meters is a nice number. So just for this case, we are just using this. But again, all of these inputs can change based on the technology, based on the location. And there was one else. Oh, and the final plot tells you this one. this water, in principle, you want to install these systems in water bodies that belong to a particular country. So in principle, your system will be protected by that country. It's a little dangerous, not impossible to go into international waters, because international waters belong to, I think, to everybody. But if you install floating PV for offshore in water bodies that belong to a country, then that country in principle will be able to protect it. So that's why we also highlight the offshore floating PV based on the country. And the color tells you here, like, of course, you can see, okay, this is the offshore floating PV for Australia. And this color tells you what is the area in kilometers square. So you want to go as blue as possible. So Australia looks good. Indonesia looks good. Then if it's greenish, I don't see this one, but I see yellowish in United States, a little in Russia, and so on. So if now with these results, I take the top 10 countries when it comes to available space, and I list them. Based on these results, I have this table. Yeah, top 10 countries. And you can see that, great, Australia is number 2. Again, Australia have a lot of land space, but it seems it also have a decent amount of space for offshore floating PV application. The key one is Indonesia, actually. Indonesia is a very good location to start offshore floating PV because the weather conditions, in comparison to other countries, is quite friendly to floating PV. But you can see there are still other countries. Now, this is the list based on available area. But at the end of the day, more than area, you care about energy production. So if you just cover once more this, I just use this basic number, 10%. If you just cover 10% of this area, this will be the energy production. You can understand that the energy production depends on the area, but also depends on the location. If you are in a location which has high irradiance, then you will be able to produce a lot of energy. So from here, you can see that indeed the key 2 locations, Indonesia and Australia, have a huge potential. And there is a lot of interest in Indonesia, actually. Again, because Australia already have plenty of land space. But there are other countries, Russia, United States, China, Brazil, and so on. You can see, for example, here, Brazil have more, in principle, more energy production than China, even though they both have the same, in principle, the same area. Why? Because these locations in Brazil experience higher irradiance than the location from China. That's why this number is roughly twice. Okay? But then again, to put things into perspective, if you think about how much of this energy is required to satisfy the electricity demand in the whole world, then you get these numbers. So you can see that actually for Indonesia and Australia, you can fully cover the whole electricity demand in the whole world because this is 10 to the 2%. So just with offshore floating PV, that's the key thing. You can actually satisfy the electricity demand based on many of these countries. And finally, when it comes to the electricity floating PV contribution towards... Oh, sorry, this is for the country itself. I apologize for that. This is for the specific country that can fully cover it by many orders of magnitudes. But when it comes to the whole world, you can see that the space from Indonesia can roughly cover for 100% of the electricity demand for the whole world, following by Australia and then the rest. So this tells you gives you an idea of how big is the potential of offshore floating PV. But again, there are many challenges. So it's just a matter of time for more technologies to be deployed, for more testing to be done in order for offshore floating PV to keep on scaling up, for systems to be deployed each time more and more for these kind of applications. So floating PV actually on its own is very exciting because from inland floating PV that now there is decent level of knowledge, now we are going more into offshore floating PV, and now there is active research on this point. Again, because there is huge potential, but there is also big challenges. Okay, so with this I wanted to finish my presentation. Thank you.
Thank you, Carlos, for the great presentation. And it was great to see that it also has potential for Australia. It was like particularly the water conservation.
Yes, yeah, correct.
And stuff like. Let's see, I think we have time for only one question because there's probably a lecture after. Because
So actually, I'm just curious in terms of when you're designing the floating floating PV. So you mentioned that there'll be quite a bit of movement on the solar panel. So in terms of the energy yield of the solar panel, let's say you're designing a solar farm. So what are the additional considerations that you have taken compared to a solar farm they've done on land. Yeah.
Yeah, thank you for that. So the key thing is where your system can survive those conditions. That's the main consideration. You want your system to last for the 25, 30 years to be floating there. So most of the manufacturers will tell you, my solution can only be used for up to this wind speed, up to this wave height. So what is very normal is before you actually do the installation, you get the historical data of that location. Let's say the historical data from the previous 50 years on the wind and wave conditions. And then you see where that particular solution can be used, or if not, then you need to aim for another one that gives you the warranty that can survive. And then the other consideration is, if there is a strong waves, then you need to, in principle, calculate what will be these mismatch losses. For inland reservoir, where the wave influence is very low, for these locations, maybe the mismatch losses will be, let's say, below 0.5%, or will be around 0.1%, so it's not that big. But if you're in a location that experiences a strong wave variation, if you use typical technologies, losses can even go up to 3%, 4%, and that's considerable. So then you can try to use other technologies where panel to panel are better attached to each other so that they move together. So these losses will be reduced. So it all depends on the site itself.
Okay, thank you.
Yeah, thanks.
Okay, in view of time, let's thank the speaker again.
Yeah, thank you so much.